Quantum mechanics is full of mind-bending experiments that challenge our understanding of reality. Here are some of the most shocking and perplexing results. 1. Double-slit experiment, wave-particle duality. Imagine you're at a shooting range, but instead of bullets, you're shooting tiny marbles at a wall. In front of this wall, there's another barrier with two narrow slits. If you shoot marbles at this barrier, most will hit the wall, but some will go through the slits and form two distinct piles on the back wall, just as you'd expect from tiny objects traveling in straight lines. Now, imagine doing the same thing with water waves. If a wave moves toward the barrier with two slits, parts of the wave pass through both slits, creating two new waves that spread out and overlap. This overlapping creates an interference pattern. Some areas where the waves combine to make bigger waves, and some areas where they cancel each other out. Now here's where it gets mind-blowing. If you fire tiny particles like electrons or photons at the two slits one at a time, you'd expect them to behave like the marbles and form two piles. But no. When you check the pattern on the back wall, you see an interference pattern like waves. Somehow, these tiny particles are behaving as if they passed through both slits at the same time and interfered with themselves. Wait, you might say, how can a single particle go through both slits at once? So, scientists got curious and placed a detector at the slits to check which slit the electron actually went through. And here's where it gets even crazier. When we watch which slit the electron goes through, the interference pattern disappears, and the electrons behave like little marbles again, forming two distinct piles. When we don't watch, they act like waves and create the interference pattern. This means that the mere act of observing changes reality itself. Somehow, electrons know when they're being watched and adjust their behavior accordingly. This experiment isn't just weird, it shatters our understanding of reality. It suggests that at a quantum level, particles don't have a definite state until they are observed. They exist in a mysterious state of probability, where they are both a particle and a wave at the same time, until something forces them to choose. Welcome to the bizarre world of quantum mechanics. 2. Quantum entanglement, spooky action at a distance. Imagine you and your best friend each have a magical pair of dice. These dice are special because no matter how far apart you are, whether you're in the same room or on opposite sides of the galaxy, whenever you roll them, they will always land on the same number. At first, you might think, well, maybe the dice were programmed in advance to match each other. But here's where it gets mind-blowing. If you decide at the last second to change how you roll your die, say by flipping it a different way, your friend's die instantly without any delay changes to match your result. Even if they are billions of light years away. This is quantum entanglement. What's actually happening? When two particles become entangled, their properties become linked in a way that defies classical physics. No matter how far apart they travel, measuring one particle immediately determines the state of the other, even if they're light years away. Albert Einstein called this spooky action at a distance because it seemed impossible. In classical physics, nothing can send information faster than the speed of light. But entangled particles act as if they communicate instantly, with no delay. Why is this so weird? Before you measure an entangled particle, it exists in a state of superposition. It has multiple possible states at the same time. The moment you measure one, the other particle instantly assumes a matching state, even if they are impossibly far apart. It seems like information is traveling instantly, which breaks the rules of physics as we know them. What does this mean? Some scientists think that quantum particles don't actually send information between them. Instead, reality itself might be deeply interconnected in a way we don't yet understand. Others speculate that this could lead to future technologies like quantum teleportation or super-secure quantum communication. Quantum entanglement is one of the biggest mysteries in physics, showing us that, at the most fundamental level, the universe doesn't behave the way we expect it to. Reality itself might be more deeply connected than we ever imagined. 3. Delayed choice experiment, future influencing the past. Imagine you're standing in front of a fork in the road. You haven't decided yet whether to go left or right, but somehow, The path you took was already determined before you even made your choice. Sounds impossible, right? Well, welcome to the delayed choice experiment, where your decision in the present seems to change what happened in the past. The classic double-slit experiment, but with a twist. You already know about the double-slit experiment, where light or electrons can act like waves, creating an interference pattern, or particles, forming two distinct lines, depending on whether we observe them. But what happens if we delay our decision to observe the particle? That's what the delayed choice experiment tests. The setup, a photon, light particle, is sent toward a beam splitter, which gives it two possible paths, left or right. The photon then travels through either one path, like a particle, or both paths at once, like a wave. Much later, after the photon has already passed the decision point, we choose whether to observe which path it took. The mind-boggling result: if we decide to measure the path, the photon behaves like a particle and follows one single route. If we decide not to measure, the photon behaves like a wave, traveling both paths simultaneously and interfering with itself. But here's the crazy part. Our decision to measure was made after the photon had already chosen its path. It's as if the photon waited for our future decision before deciding how it behaved in the past. What this means? This suggests that the present can affect the past at a quantum level. Reality isn't set in stone. It seems to be flexible, adjusting to observations even after events have already happened. The big questions: does this mean time doesn't work the way we think it does? Is the past not fixed, but rather determined by future choices? Does our act of observation actually shape reality itself? Nobody fully understands this yet, but one thing is clear: quantum physics doesn't just defy our logic. It rewrites the rules of time and reality. Imagine you're playing a video game where your character is standing in front of two doors. The game doesn't decide what's behind the doors until you actually open one. Before that moment, both possibilities exist at the same time. Now, take that concept and apply it to the real world. That's the bizarre reality of quantum superposition, where things don't have a definite state until they are observed. Schrödinger's cat. A thought experiment to explain this weirdness. Physicist Erwin Schrödinger came up with a now-famous experiment involving a cat, a box, and a little bit of quantum madness. The setup: imagine putting a cat inside a sealed box. Inside the box, there's a tiny radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that breaks a vial of poison, killing the cat. If the atom doesn't decay, the cat stays alive. The quantum weirdness. In the world of classical physics, the cat is either dead or alive, even if you haven't opened the box. But in quantum mechanics, until you open the box and check, the cat is in a superposition of both states, alive and dead at the same time. The moment of observation. The moment you open the box, reality decides whether the cat is dead or alive. Before that, the cat is in a weird in-between state, neither fully one nor the other. Why is this so crazy? At a quantum level, particles don't have a definite state until they are observed. Electrons, for example, can be in multiple places at once until we measure them. Superposition is what makes quantum computers so powerful. They use qubits that can be both 0 and 1 at the same time, unlike normal computer bits that are either 0 or 1. The big questions: does observation create reality? Is the universe a sea of probabilities until we interact with it? What if, in some alternate reality, the cat really was both alive and dead? Quantum superposition challenges everything we know about reality, suggesting that the universe doesn't decide what's real until we look. 5. Quantum Zeno effect. Freezing time by observation. Imagine you're watching a boiling pot of water. Normally, it should start bubbling after a while, right? But what if, just by constantly staring at it, you could stop it from boiling at all? Sounds ridiculous, but in the quantum world, this kind of thing actually happens. The quantum Zeno effect. A watched pot never boils. The quantum Zeno effect is the bizarre idea that if you continuously observe a quantum system, you can freeze it in place and prevent it from changing. How it works: quantum particles are always changing. Normally, an unstable quantum system, like an excited atom, will eventually change state. For example, a radioactive atom will decay into another form after some time. But if you keep checking on it, if you keep measuring the atom's state over and over again in quick succession, it stays in its original state and doesn't change. It's as if the act of observing resets the countdown, preventing the atom from decaying. This means observation can freeze change. The more frequently you observe a system, the slower it evolves. In theory, if you observe it infinitely often, the change never happens at all. Why is this so crazy? Time itself seems to slow down at the quantum level. This suggests that observation doesn't just reveal reality, it controls it. The idea challenges our fundamental understanding of cause and effect. What does this mean in real life? Scientists are exploring the quantum Zeno effect for quantum computing and communication because it could help stabilize quantum systems. Some even speculate it could lead to new ways of controlling time-dependent processes at the atomic level. The big question: if watching something stops it from changing, does that mean reality itself is shaped by awareness? Quantum mechanics keeps proving that the act of looking at something might actually change its fate, or even freeze time itself. 6. Quantum tunneling, particles passing through barriers. Imagine you're running full speed toward a solid wall. In the normal world, you'd smash right into it and bounce off, maybe with a broken nose. But what if, just by sheer randomness, you suddenly appeared on the other side of the wall without breaking it? Sounds impossible, right? Well, in the quantum world, this actually happens. It's called quantum tunneling. What is quantum tunneling? At a tiny quantum level, particles don't behave like tiny billiard balls. Instead, they act like waves that spread out over space. This means that instead of being confined to one place, a particle has a probability of being found in multiple locations at once. Now, normally, if a particle encounters a barrier that it doesn't have enough energy to cross, classical physics says it should just bounce back, like a ball hitting a wall. But here's where it gets weird. Instead of stopping, the quantum particle has a small probability of tunneling through the barrier and appearing on the other side. It doesn't go over the barrier, it doesn't break through. It just vanishes on one side and reappears on the other. It's as if the particle said, "Meh, physics is optional." Why is this so mind-blowing? This defies classical logic, where objects should never pass through barriers they can't overcome. It suggests that particles don't travel in a fixed, predictable way, but instead, they explore multiple possibilities at the same time. This is one of the key reasons the sun keeps burning, because nuclear fusion in stars relies on quantum tunneling for atoms to get close enough to fuse. Real-world applications. Quantum tunneling isn't just a theoretical curiosity. It powers real technologies. Flash memory, like USB drives, works because electrons tunnel through tiny barriers inside circuits. Scanning tunneling microscopes, STM, allow us to see individual atoms by using tunneling electrons. Nuclear fusion in the sun wouldn't happen without tunneling, meaning we owe our existence to this bizarre quantum trick. The big questions. If quantum particles can teleport through barriers, what does that say about our understanding of space and matter? Could future technologies harness quantum tunneling for teleportation-like devices? Quantum tunneling is proof that at the smallest scales, particles don't care about the rules we think they should follow. 7. Wheeler's delayed choice quantum eraser, changing the past. Imagine you throw a basketball toward a hoop, but somehow the decision about whether the ball actually went through the hoop or missed is made after it has already landed. Sounds crazy, right? Well, in the quantum world, something even stranger happens. An experiment suggests that our choices in the present can change what happened in the past. Wheeler's delayed choice quantum eraser. This is a mind-bending upgrade of the double-slit experiment, where particles behave like both waves and particles depending on whether we observe them. The setup, brace yourself, it gets wild. A photon light particle is fired toward a beam splitter, which sends it down two possible paths. Normally, the photon would act like a wave, traveling both paths at once and creating an interference pattern. However, if we observe which path it took, it collapses into a particle-like state and follows just one path. So far, this is just the usual quantum weirdness. But now, here's the crazy twist, the delayed choice part. Scientists set up detectors far away from the slits, which means the photon has already passed through the slits before they decide to measure it. Now, here's the insane part. If they later choose to observe which path the photon took, it acts like a particle. If they choose not to observe, it acts like a wave. But the photon had already passed the slits. How could our choice to measure it after the fact change its earlier behavior? The mind-boggling conclusion. It's as if the photon waited in the past for us to decide its fate in the future. Our choice to measure after it has already passed the slits seems to determine what it did before it was measured. Did the future change the past? Why is this so freaky? It shatters our common-sense idea of cause and effect. Events in the future appear to influence what happened in the past. It suggests that reality might not be fixed until it's observed, meaning the past itself could be uncertain. Some physicists wonder, is time an illusion? Is everything predetermined? Or do we create reality as we observe it? What does this mean for reality? The Wheeler's delayed choice experiment suggests that time in quantum mechanics doesn't behave the way we think it should. Reality might be much weirder than a simple past-to-future flow. It could be that the future helps shape the past. If this doesn't make your brain explode, I don't know what will. 8. Bell's theorem experiments. Non-locality confirmed. Imagine you and your best friend each have a pair of magical dice. You're on Earth and your friend is on Mars. You both roll your dice at the exact same moment, without any way to communicate. Now, here's the weird part. Whenever you check your results, your dice always match, even though there was no way for them to talk to each other. It's as if the dice were instantly connected, no matter how far apart they were. This is the essence of Bell's theorem experiments, which confirmed that the universe is deeply interconnected in ways we don't fully understand. What is Bell's theorem? Bell's theorem was proposed by physicist John Bell in the 1960s to test whether reality follows local realism. The idea that locality, things can only influence each other at the speed of light or slower. Realism, objects have definite properties before we measure them. Quantum mechanics, however, suggests otherwise, that particles can be entangled and influence each other instantly across vast distances. Bell's theorem provides a mathematical test to check whether reality is truly local or not. The experiment that shocked the world, scientists created pairs of entangled photons and sent them to two far-apart detectors. Each photon was measured for a specific property, like polarization, but the detectors were far enough apart that no signal could travel between them in time. If local realism were true, the photons should behave independently, and their measurement results should follow certain statistical limits, called Bell's inequalities. But reality disagreed. The results showed that the photons were still mysteriously linked, even across vast distances. What this means? Local realism is false. The universe does not behave in a way that can be explained by simple, independent particles with predetermined properties. Quantum entanglement is real. Measuring one particle instantly affects the state of its entangled twin, no matter how far apart they are. Non-locality is a fundamental feature of the universe. Something deeper than space and time might be connecting distant particles. The big questions: does information travel faster than light? If so, it breaks Einstein's relativity, which says nothing can exceed the speed of light. Is the universe fundamentally interconnected in ways we don't understand? Does reality exist before we measure it? Bell's experiments confirmed quantum entanglement beyond any doubt, proving that reality is stranger than anyone expected. In other words, the universe doesn't play by our rules, it plays by quantum rules. 9. Quantum teleportation, information transfer without matter movement. Imagine you're holding a book in your hands. You want to send this book to your friend on Mars, but instead of physically sending it, you somehow destroy it on Earth and have an exact copy appear instantly on Mars. Sounds like sci-fi, right? Well, in the quantum world, something very similar is already happening. It's called quantum teleportation. What is quantum teleportation? Quantum teleportation isn't about sending actual physical objects, like Star Trek's teleporters. Instead, it allows the instantaneous transfer of quantum information between two distant particles, without sending anything through space. The key to this is quantum entanglement, a mysterious connection between two particles no matter how far apart they are. How it works? Step by step. Start with two entangled particles. One stays with you on Earth, and the other is sent far away to Mars, for example. Introduce a third particle. This is the information, like the book you want to teleport. Perform a quantum measurement on the third particle and your entangled Earth particle. This destroys the original information. You lose the book here. Instantly, the information appears in the entangled particle on Mars, without anything physically traveling there. Even though no physical object moves, the quantum state is perfectly recreated at the distant location, as if the original state jumped across space. Why is this so mind-blowing? No physical travel required, just information being transferred through entanglement. Faster than light connection? The transfer of quantum states happens instantly, which seems to break the speed of light limit, but doesn't actually send usable information faster than light due to quantum limitations. It's already been done. Scientists have successfully teleported quantum states between particles across kilometers, even using satellites in space. Real-world applications. Quantum computing allows for instant data transfer between quantum processors. Ultra-secure quantum communication. Quantum teleportation can enable unhackable data transfer because any eavesdropping would instantly disrupt the system. Possibly a step toward future teleportation? While teleporting humans is pure science fiction, for now, quantum teleportation proves that instantaneous transfer is possible at a fundamental level. The big questions. If information can teleport, does that mean space itself is just an illusion? Could we ever teleport more than just quantum states? Maybe even matter? Does this prove that everything in the universe is somehow interconnected? Quantum teleportation is real, it's happening right now in labs, and it could revolutionize the way we think about communication, computing, and even reality itself. 10. Time crystals, a new form of matter defying thermodynamics. Imagine you have a magical clock. No matter what happens around it, whether you shake it, freeze it, or even stop time itself, it keeps ticking endlessly without using any energy. Sounds like something out of a sci-fi movie, right? Well, welcome to the bizarre world of time crystals, a new form of matter that defies the normal rules of physics. What are time crystals? In normal physics, everything eventually runs out of energy. If you spin a top, it slows down and stops due to friction. If you heat up an object, it eventually cools down. This is because of the second law of thermodynamics, which states that systems naturally move toward disorder, entropy. But time crystals break this rule. They oscillate or move in a repeating cycle forever without using energy. Instead of finding a lowest energy resting state like all normal materials, time crystals stay in a state of perpetual motion at the atomic level. How do they work? They don't exist in space, but in time. Normal crystals, like diamonds, have a repeating spatial structure. Time crystals have a repeating time-based structure. They cycle between different states over time without consuming energy. They exist in a state of quantum weirdness. They use quantum entanglement to maintain their cycle. Even if you try to stop them, they continue switching states endlessly. They were first created in a lab in 2016. Scientists at Harvard and Google used lasers and quantum computers to create real-time crystals. The experiment showed that atoms could switch back and forth in a stable, repeating motion without any external input. Why is this so mind-blowing? It challenges the fundamental laws of physics. It violates traditional thermodynamics, which says all systems should eventually settle down. It could revolutionize quantum computing. Time crystals might be used to store quantum information in ways never thought possible. It hints at a deeper, hidden order in the universe. Are time crystals proof that there's something beyond our understanding of energy and matter? Real-world applications: quantum computing. Time crystals could help build more stable quantum computers that don't require constant energy input. New materials and energy storage could lead to materials that store energy in never-before-seen ways. Understanding the nature of time itself. If time crystals defy entropy, does that mean time isn't as irreversible as we think? The big questions. Does this mean perpetual motion is possible at the quantum level? Could time crystals help us understand time travel or parallel universes? Is time itself an illusion, with deeper patterns we haven't discovered yet? Time crystals are one of the most bizarre discoveries in modern physics, proving once again that the universe is way stranger than we ever imagined. Quantum mechanics isn't just weird, it's a total reality-breaking experience. It challenges everything we thought we knew about time, space, and even existence itself. Now, the real question is, are we ready to accept how truly bizarre our universe is? Quantum mechanics doesn't just challenge our understanding of the universe, it rewrites reality itself. The more we study it, the more we realize that the rules we thought were unbreakable don't actually exist at the quantum level. Particles exist in multiple states at once until observed. Information can teleport without moving. The future might affect the past. Reality could be deeply interconnected beyond space and time. What if the world we see is just a shadow of a much deeper reality? What if consciousness itself plays a role in shaping the universe? The real beauty of quantum mechanics is that it reminds us how little we actually know, and that the strangest possibilities might just turn out to be true. So maybe, just maybe, the universe isn't just weirder than we imagine. It's weirder than we can imagine. Quantum science is filled with mind-bending concepts beyond just the famous experiments. Here are more fascinating topics that push the boundaries of our understanding of reality. Quantum vacuum fluctuations. How the universe is never truly empty. Imagine you're in a completely silent room. No sound, no movement, absolute nothingness. But suddenly, tiny whispers appear and disappear so fast that you barely notice them. That's exactly what happens in the quantum vacuum. Even in what we think is empty space, tiny particles keep popping in and out of existence. The weirdness of nothing. In everyday life, when we remove everything from a box, we expect it to be completely empty. But in quantum physics, even when you remove all matter, all light, and all energy, space is never truly empty. Instead, tiny particle-antiparticle pairs randomly appear and vanish so quickly that they can't be directly observed. These are called vacuum fluctuations. Think of it like a quantum magic trick. Particles appear out of nowhere, then disappear before anyone can catch them. How is this possible? Thanks to Heisenberg's uncertainty principle, quantum physics allows for brief violations of the law of conservation of energy, meaning that for an extremely short time, energy can appear from nowhere before vanishing again. It's like the universe has a secret cheat code that lets it borrow energy, as long as it returns it quickly enough. Why is this important? 1. Hawking radiation and black holes. These fluctuations near a black hole's edge can steal energy from it, causing the black hole to slowly shrink over time. 2. Big Bang and the origin of the universe. Some theories suggest the entire universe might have emerged from quantum fluctuations. 3. Casimir effect. Invisible quantum forces. Two very close metal plates can be pulled together just because of these quantum fluctuations, proving that empty space has energy. The big takeaway: even in the deepest void of space, reality is never truly empty. The universe is always bubbling with quantum energy, creating particles out of nothing for the briefest moments. So, the next time someone asks, "What happens in empty space?" you can confidently say, "Nothing and everything at the same time." Quantum decoherence. Why you never see a cat that's both alive and dead. Imagine you're playing a video game where your character is in two places at the same time. But the moment you hit record to show your friend, the character instantly chooses only one position. That's what happens in the quantum world with quantum decoherence. It's why we don't see objects existing in multiple states at once, even though quantum physics says they should. Why does superposition disappear? At the quantum level, particles don't have a fixed state until observed. They exist in superposition, being in multiple places or states at once. Electrons can spin in two directions at the same time. Atoms can be in two locations at once. Schrödinger's cat can be both alive and dead. So why don't we see this in real life? Why doesn't your phone float in two places until you look at it? The answer: quantum decoherence. How decoherence works. Think of quantum superposition like a delicate soap bubble. In isolation quantum systems, the bubble is stable. When it interacts with the environment, air, dust, photons, it pops. Particles are constantly interacting with their surroundings, air, heat, light, even cosmic radiation. This interaction scrambles the quantum states, forcing them to collapse into a single classical reality. The more particles involved, the faster decoherence happens. This is why tiny electrons can be in superposition but large objects like a cat or a chair cannot. They interact with too many things around them. Why is decoherence so important? 1. Explains why we see a classical world. It tells us why we never see large objects in quantum weirdness. They lose their quantum behavior too fast. 2. Key to quantum computing. Quantum computers rely on superposition to work, but decoherence can destroy that information. Scientists are working on ways to shield quantum bits, qubits, from decoherence. 3. Hints at the nature of reality. Does decoherence mean wave function collapse isn't real and superpositions just fade away instead? Some theories suggest parallel universes where all possible outcomes still exist. The big takeaway: quantum superposition is fragile. The moment a quantum system interacts with its surroundings, decoherence forces it to choose one state. That's why we never see a blurry, overlapping world of possibilities. Only one solid version of reality. So, the next time you wonder why you don't see ghosts of possible realities floating around, thank quantum decoherence. Quantum gravity, the missing link between the big and the small. Imagine trying to mix water and oil. No matter how hard you shake the bottle, they just won't blend. That's exactly what's happening with quantum mechanics and general relativity, two fundamental theories of physics that just don't fit together. Physicists have been struggling for decades to unify them under a single framework called quantum gravity, a theory that could finally explain everything. The clash of two universes. Quantum mechanics, tiny scale, governs the world of particles, atoms, and photons. Reality is uncertain. Things exist in multiple states and randomness rules. General relativity, cosmic scale, governs the large-scale universe, planets, stars, black holes. Reality is smooth and predictable, and gravity bends space and time. But these two theories contradict each other. Quantum mechanics says space-time is fluctuating and uncertain at tiny scales. General relativity says space-time is smooth and continuous. Something is missing. Quantum gravity is the answer we need. The biggest mysteries quantum gravity could solve. 1. What happens inside a black hole? General relativity predicts an infinite singularity, but infinity is a sign that something is wrong. Quantum gravity could reveal what's really inside black holes. 2. What happened before the Big Bang? Quantum gravity could explain what existed before time and space began. 3. Does gravity come in tiny particles? If other forces, electromagnetism, weak, strong, have quantum particles, does gravity have one too? Some theories predict a mysterious particle called the graviton. Leading theories of quantum gravity, string theory, suggests that all particles, including gravity, are tiny vibrating strings. Requires extra hidden dimensions beyond the 3D world we see. Loop quantum gravity suggests that space-time itself is made of tiny, discrete loops, like pixels on a screen. Holographic principle. The idea that our universe is a 3D projection of information stored on a 2D surface, like a cosmic hologram. The big takeaway. Right now, we have two powerful but incomplete theories: quantum mechanics and general relativity. Quantum gravity is the missing puzzle piece that could finally unite them, leading to the ultimate theory of everything. When we crack the code of quantum gravity, we may finally understand the true nature of reality itself. Many worlds interpretation. Every quantum choice creates a new universe. Imagine you're at a crossroads. You can either go left or right. In the normal world, you pick one path and that's the only reality. But in the quantum world, both choices happen. One version of you goes left and another version of you goes right in a parallel universe. This is the many worlds interpretation, MWI, of quantum mechanics, which suggests that every possible outcome of a quantum event actually happens, each in its own separate universe. How does it work? In quantum physics, particles exist in superposition. They can be in multiple states at once. When you measure a particle, you force it to choose a state. But MWI says it doesn't actually choose. All possible outcomes happen, splitting reality into different branches. For example, you flip a coin. In one universe, it lands on heads. In another universe, it lands on tails. The same thing happens for every decision, every quantum event, every moment. Why is this so mind-blowing? 1. There could be infinite versions of you. A version that made every possible choice differently. A universe where you became a billionaire. A universe where dinosaurs never went extinct. 2. It removes randomness from quantum mechanics. Instead of saying, the universe picks an outcome at random, it says, all outcomes exist, just in different universes. 3. It challenges our idea of reality. Are we just one of countless parallel worlds? Could we ever interact with another version of ourselves? Is there any evidence? Right now, we can't test the many worlds interpretation directly, but it explains quantum mechanics without needing wave function collapse. One of the biggest mysteries in physics. Some physicists believe quantum computers might eventually reveal clues about parallel universes. The big takeaway: if the many worlds theory is true, every possible version of reality exists somewhere. Every choice, every possibility, every what if is real in another universe. So in some other world, you're living your dream life, and in yet another, you're a talking fish. Quantum cryptography, the future of unhackable communication. Imagine you're passing secret notes to your friend. But every time someone tries to peek at the note, the ink disappears instantly. That's how quantum cryptography works. It uses the laws of quantum mechanics to create unbreakable encryption, making it impossible for hackers to eavesdrop without being detected. How does it work? Traditional encryption relies on math, but with enough computing power, hackers can break it. Quantum cryptography relies on the laws of physics, making it fundamentally secure. The key technology behind this is quantum key distribution, QKD1. Two people, Alice and Bob, want to share a secret message. 2. They send quantum particles like photons that carry encryption keys. 3. If a hacker tries to intercept the photons, quantum mechanics forces them to change, alerting Alice and Bob. 4. The message is either perfectly secure or discarded if tampered with. No in between. It's like a magic lock that breaks if someone even tries to touch it. Why is this so powerful? Completely unhackable, no current or future supercomputer can crack quantum encrypted data. Eavesdroppers can't hide any attempt to spy changes the message itself. Used in real-life, countries and tech companies are already testing QKD for ultra-secure communication. The future of quantum security. Governments are investing in quantum-safe encryption to protect against cyber threats. Quantum internet could make hacking completely obsolete. Scientists are working on global quantum networks, secure communication from Earth to space. The big takeaway: quantum cryptography isn't just a cool idea, it's the future of cybersecurity. As quantum computers grow more powerful, traditional encryption will become useless. But with quantum encryption, your secrets will remain truly unbreakable. Quantum consciousness. Is your mind a quantum machine? Imagine your brain is like a supercomputer, but instead of just using electricity, it taps into quantum mechanics. Where thoughts exist in superposition, decisions are entangled, and consciousness itself may transcend time and space. This is the idea behind quantum consciousness, the theory that the human mind might not just be a biological machine but instead a quantum system. What does this mean? In classical neuroscience, the brain is just a network of neurons firing electrical signals. But some scientists believe this explanation isn't enough to explain things like free will. Are our choices truly ours? Intuition. How do we sense things before they happen? The mystery of consciousness. How do we even experience reality? Quantum mechanics introduces strange possibilities like superposition and entanglement that might help explain how the brain works. The leading theory, orchestra quantum brain hypothesis. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that quantum effects occur inside tiny structures in the brain called microtubules. Microtubules are small structures inside neurons that help with processing information. Their theory suggests that quantum computations happen inside these microtubules, allowing the brain to function beyond classical physics. Some even speculate that consciousness might be linked to the fabric of the universe itself. If true, this could mean: first, your mind exists in a quantum state. Could thoughts exist in superposition, allowing us to think of multiple things at once? Second, quantum entanglement could explain telepathy. Could minds be connected in ways we don't understand? Third, consciousness might be beyond the brain. Some suggest that death doesn't mean the end of consciousness. Instead, it returns to the universe. Skepticism and reality check. Right now, there's no direct evidence that the brain uses quantum mechanics. The brain is warm and wet, and quantum effects usually occur in extremely cold and isolated environments. But some experiments hint that quantum processes might play a role in biological systems, like bird navigation and photosynthesis. The big takeaway: we don't yet know whether quantum physics plays a role in consciousness, but if it does, it could change everything we know about the mind, free will, and even life after death. So, is your mind just a biological computer? Or is it something much deeper, entangled with the universe itself? Bose-Einstein condensate, the fifth state of matter. Imagine you have a group of people dancing randomly in a club, everyone moving in their own chaotic way. Now, suddenly, a mysterious force makes them all move in perfect sync, as if they became a single being. That's exactly what happens in a Bose-Einstein condensate, BEC. A bizarre fifth state of matter where individual atoms merge into one giant quantum entity, behaving like a single superparticle. What is a Bose-Einstein condensate? In everyday life, we see four common states of matter. 1. Solid ice. 2. Liquid water. 3. Gas steam. 4. Plasma, lightning. But in 1995, scientists created a new state, Bose-Einstein condensate, BEC, by cooling atoms to nearly absolute zero, minus 273.15 degrees Celsius. When this happens, the atoms stop behaving like individual particles and start acting as one unified quantum wave. almost like a superatom. How does this work? 1. Atoms normally move randomly like a chaotic crowd. 2. But at extremely low temperatures, they lose their individuality. 3. Instead of bouncing around, they merge into a single quantum state, behaving like one entity. It's like turning thousands of individual instruments into one perfect symphony. Why is this so mind-blowing? Quantum mechanics on a macroscopic scale. Normally, we only see quantum effects in tiny particles, but Becks bring quantum weirdness into visible size. Slowest matter ever observed. Atoms in a BC move so slowly they're practically frozen in time. Used to simulate black holes and dark matter. Scientists use Becks to study the weird physics of black holes, time travel, and even the early universe. The big takeaway: a Bose-Einstein condensate is like a quantum ghost, where thousands of atoms become one and behave like a single wave. It's a glimpse into the strange, unified nature of reality at its most fundamental level. So, next time you think you're feeling in sync with someone, remember, atoms in a BEC are taking syncing to a whole new quantum level. Quantum supremacy, when quantum computers beat classical ones. Imagine you challenge the world's fastest supercomputer to solve a maze. The supercomputer goes step by step, testing paths one at a time. But a quantum computer? It explores all paths simultaneously and finds the solution in an instant. This is the power of quantum supremacy, the moment when quantum computers outperform even the best classical computers at certain tasks. What is quantum supremacy? Quantum supremacy occurs when a quantum computer completes a problem that a classical computer would take an impractically long time to solve. In 2019, Google's quantum computer, Sycamore, performed a calculation in 200 seconds that would take the world's best supercomputer 10,000 years. How do quantum computers work? Classical computers use bits, 0 or 1. Quantum computers use qubits, which can be 0, 1, or both at the same time, thanks to superposition. This allows them to process multiple possibilities simultaneously, solving problems exponentially faster. It's like reading every book in a library at the same time instead of one by one. Why is this so revolutionary? Breaks traditional encryption. Quantum computers could crack modern encryption in seconds, forcing the world to invent quantum-safe security. Revolutionizes science and AI. Quantum simulations could discover new materials, medicines, and AI algorithms faster than ever. Solves problems we never could before. Could help model black holes, time travel, or even simulate the entire universe. The big takeaway: quantum supremacy is the first step into the future of computing, where problems that once seemed impossible become trivial. While we're still in the early stages, the world is racing to build powerful quantum machines that could change everything. So, are quantum computers the future of intelligence? Or are they the beginning of something even bigger than we can imagine? Quantum metrology, measuring the unmeasurable. Imagine you have a ruler so precise that it can measure the width of a single atom, or even detect the tiniest vibrations of spacetime itself. This is the power of quantum metrology, which uses the bizarre principles of quantum mechanics to measure things far beyond the limits of classical instruments. What is quantum metrology? Traditional measuring devices like rulers, thermometers, or even atomic clocks have limits in precision due to noise and randomness. But quantum mechanics allows us to detect minuscule changes in time, gravity, and electromagnetic fields, achieve precision far beyond classical physics. How does it work? Superposition. Quantum states can exist in multiple configurations at once, increasing sensitivity. Entanglement. Linked particles share information instantly, improving measurement accuracy. Quantum interference. Tiny phase shifts can be detected with insane precision. Using these principles, quantum metrology helps us create the most accurate clocks ever. Atomic clocks using quantum effects are so precise that they lose only 1 second every 30 billion years. Detect gravitational waves. The LIGO experiment detected ripples in spacetime from black hole collisions thanks to quantum metrology. Measure tiny magnetic fields for brain activity. Quantum sensors can detect neural signals in the brain, leading to advanced medical breakthroughs. Improve GPS accuracy to the centimeter level. Future GPS could be thousands of times more precise using quantum-enhanced sensors. The big takeaway: quantum metrology is redefining how we measure reality itself. From detecting black holes to mapping brain activity, it's unlocking a new level of precision that could change science, medicine, and technology forever. Are we on the verge of measuring the very fabric of the universe itself? Quantum biology, life's quantum secrets. Imagine a bird navigating thousands of miles with perfect precision, or a plant absorbing sunlight with near 100% efficiency. It turns out these natural processes may be tapping into quantum mechanics, the same rules that govern subatomic particles. Welcome to quantum biology, the idea that life itself might rely on quantum effects to function in ways we never imagined. How does quantum biology work? While biology is usually explained with classical chemistry, some biological systems are so efficient that they seem to defy traditional physics. Quantum effects might be the hidden answer. Quantum tunneling in DNA mutations. Electrons can teleport across molecular bonds, possibly affecting genetic mutations. Quantum superposition in photosynthesis. Plants absorb sunlight with nearly 100% efficiency. Quantum mechanics may help energy travel in multiple paths simultaneously until it finds the best route.
Quantum Entanglement in Bird-Navigation.
Some birds, like the European robin, use Earth's magnetic field to migrate. Experiments suggest that entangled electrons in their eyes might create a biological quantum compass. Quantum sensing in smell. Some scientists believe we recognize smells not just by shape, but by detecting quantum vibrations in molecules. Why is this so mind-blowing? It suggests that quantum physics isn't just for the microscopic world. It affects living organisms too. It could revolutionize medicine, helping us understand biological processes at a quantum level. It challenges the idea that life is purely classical. What if consciousness itself has quantum origins? The big takeaway: quantum biology is unlocking a hidden layer of nature, revealing that life may be deeply connected to the quantum universe. Could this mean that our very existence is built on quantum principles?